Hello, calculus fans. We're now going to talk about parametric surfaces. Essentially what we're going to be doing now is parameterizing surfaces, whereas before we parameterized curves. So we've talked about graphs that are functions of two variables. Graphs like z equals f of x comma y. What we're going to do now is use vector functions to describe more general surfaces. Now before, we used vector functions to define space curves using a single parameter. Now we're going to describe a surface using a vector function of two parameters, u and v. So let's suppose that r of u comma v looks like this with component functions x, y, and z, and these are all functions of u and v. This is a vector-valued function defined on a region D in the UV plane. So, x, y, and z are the component functions of R and are functions of the two variables u and v. Those are the parameters. So we're going to define the set of all points x, y, and z in space such that x is equal to x of uv, y is equal to y of uv, z is equal to z of uv. And uv is going to be chosen from a set D. This thing is going to be called a parametric surface. The equations that define x, y, and z are called parametric equations of the surface. Every time we pick a point uv, it gives us a point on the surface. If we make all possible choices, then we get all of S. Another way of thinking about this is that the surface S is traced out by the tip of the position vector r of uv as uv moves throughout D. Let's look at a picture now of a parametric surface. This is an example of a parametric surface. So the surface is on the right side. D is the domain in the UV plane, and as you pick a point in the set D, there's a corresponding point in S. So as you move that point UV around, then the point on the surface will be changing also. Okay, that's all for now.